CETIC performed an experiment on the Bonfire testbeds to validate the scalability of continuous security monitoring in a cloud environment. This work was funded under the European FP7. In the early days of the Internet, an e-merchant constructed an e-commerce site and hosted it in an infrastructure that he fully owned. Protecting the e-merchant system mostly meant implementing security mechanisms to let customers access the desired goods while keeping ill-intentioned people outside the system. Implementing the needed security required the interaction between several people with different IT roles. Making the e-commerce site secure required work from the architect, who needed to conceive an architecture with the appropriate security features, the system administrator, who must configure hardware and software to prevent unauthorized access, the database administrator, who was in charge of protecting the data, and the developer, who needed to program the e-merchant site to prevent security breaches. As a result, a change in security policies often turned out to be costly and also quite risky. With the advent of cloud technologies such as hardware virtualization, data centers have emerged to provide on-demand adaptable computing power and storage. This has created a new consumption paradigm for computing where computing power and digital storage are seen as utilities just like electricity or telecommunication services. Going back to our e-merchant example, thanks to cloud computing, our e-merchant does not need to acquire more hardware servers only for few periods of intense customer visits. Instead, he can decide in near real time to rent additional servers from a data center for a short period to be capable to absorb an upcoming intense customer load, for example, during the time of an advertisement campaign. In this new consumption paradigm, the old security implementation model becomes quite impractical. Instead, a single security manager should handle multiple security aspects used to be controlled by different IT roles. With regards to cloud security services, architectures based on Policy Enforcement Point and Policy Decision Point, PEP-PDP for short, have emerged. A PEP-PDP architecture centralizes the specification of security policies in one file of the system, and it can then control the security of the application even when the system scales up or down based on the demand. In addition, the PEP-PDP architecture enables changing the security policies while the system and application are in operation, without a need to restart the system. Moreover, the PEP-PDP model not only protects the system from attacks, but also provides a convenient way to control how customers use the service. Let's imagine that our e-merchant wants to build a music streaming website. As you may know, those services used to control how users listen to music according to various criteria: the number of songs per day or month, the number of songs per user, the country of the customer, etc., etc. Based on this use case, solution architects may want to know the impact of usage control on performance in cloud computing infrastructure. On which criteria should they design their infrastructure?
In order to answer this question, we needed to conduct a series of tests where we can control many environment variables. Multiple architectures were tested where components were deployed in various locations. Initially, clients target their request to a single application server, connected to a PDP server on the same testbed. Alternatively, a load balancer can distribute requests among several app servers. Those can be deployed on separate testbeds, each with their own PDP servers. In order to load test the PDP server on the EPCC testbed, many instances of the application server redirect the security request to that single PDP. Yet another configuration for reducing the network latency between the application and the PDP is to deploy them on the same server. Thanks to Bonfire, all these configurations were easy to test on heterogeneous testbeds. Results of our experiment demonstrate that every possible configuration for PDP deployment scaled appropriately, response time in a matter of milliseconds. However, one configuration brought up a major limitation due to network latency, in particular when a single PDP server attempts to respond to app servers on multiple testbeds. Before our experiment, solution architects wondered about how to efficiently deploy and implement a scalable usage control service in a cloud environment. Bonfire exec comes with test results, best practices, and advice that can help out solution architects optimize a cloud architecture for a scalable usage control application. For more information, do not hesitate to contact us at CETIC.